Alright, AP Chem, this is your video lecture for Chapter 6, Section 4. We're talking about standard enthalpies of formation. Okay, standard enthalpies of formation is going to be represented by delta H subscript F for formation, and then the standard enthalpy part, the standard is going to be represented by the null symbol there, or it looks like the degree symbol. So delta HF null, that's standard enthalpy of formation. Now, the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements, the elements that make it up, the formation of 1 mole of the compound from its elements with all the substances in their standard states, okay, how they normally occur, is what's known as the standard enthalpy of formation, right? This compound is forming. There's going to be a change in enthalpy. All of those products are not going to be the same energetically as the things that combine to make them. So there's either going to be an absorption of energy or release of energy. So there's going to be some sort of change in enthalpy. And so when something is forming, we call it the standard enthalpy of formation. In general, there are just some conventional definitions for standard states. This is just by convention, the things that everyone agreed on just to make it easier. So for a compound, something that's made of different elements, if it's a gas, okay, the pressure is exactly 1 atmosphere. Exactly. If it's a solution, the concentration is exactly 1 molar. If it's a pure substance, it's going to be a liquid, a liquid or solid state. It's going to have a standard standard enthalpy of formation of 0. So anything that you see like N2 or K existing at its standard condition, standard temperature and pressure, it's going to have a standard enthalpy of formation of 0. So if we use the combustion of methane, CH4, we use that as an example. Let's show what's going on here. So in this reaction, we have methane, CH4, and oxygen, O2. So you need 1 methane, 2 O2s. And in order for them to combust, rearrange, and form carbon dioxide and water, you're going to have the hydrogens remove themselves from the carbon. So we have a carbon and 4 hydrogens. These these oxygens right here, they don't quite have to split yet, but we do have this plate of elements available for use here. Now, the movement from CH4 to a carbon and 4 H's is going to require some energy. Okay, we're going to have 75 kilojoules. Now, contrary-wise, this is a pure substance. This is just O2. So this delta H is 0. Okay, by definition, if it's just a pure substance, pure element, O2, O3, whatever you're looking at, N2, K, so it's going to have the delta H of 0 kilojoules. Now, in step 2, when these things start to rearrange, we're going to take this 1 carbon and hook it up with 2 oxygens to make CO2. Okay, this change in enthalpy is going to be negative, though. This is going to be a negative enthalpy, negative 394 kilojoules. This combination right here is going to have a delta H of negative 394 kJ. The standard enthalpy formation of the water, the H2O, is going to be negative 572 kilojoules. All right. Now, representing that up here in this equation, the delta H of the entire reaction, okay, we have negative 75 kJ plus 0. Okay, this is a 0. We also have negative 394 kJ, and we also have negative 572 kJ. Summed up, it's going to be negative 891 kilojoules. All right, so when you come up against enthalpy calculations, there's going to be a system to follow, just like in Section 3 in Hess's Law. If you need to reverse a reaction for the same types of reasons you'd need to when using Hess's Law, the magnitude of delta H stays the same, but its sign changes, just like in Hess's Law. And when the balanced equation for a reaction is multiplied by an integer to make sure that there's the correct number of reactants and products, the value for delta H for that reaction must be multiplied by that same integer, just like in Hess's Law. But when we move forward, the change in enthalpy for a given reaction can be calculated from the enthalpies of formation of the reactants and products. So let's get all of the enthalpies of formation for all the reactants and all of the products. Get them out, get them on your paper, get them written down. Now you're going to sum all of the enthalpies of formation of the products. Okay, that's what this symbol means right here, this capital sigma. You're going to sum all of the delta HF, okay, the enthalpies of formation of all of the products. You're going to sum all of the enthalpies of formation of the reactants, and then you're simply going to find the distance. You're going to subtract the enthalpies of formation of the products. You're going to subtract the enthalpies of formation of the reactants from the enthalpies of formation of the products, and that will give you the overall enthalpy of formation, change in enthalpy for the reaction overall. Now remember, elements in their standard states that are not included in the delta H for the reaction because the delta H formation for an element in its standard state is 0. Okay, remember, when you have a pure element, H2, N2, O2, F2, something like that, it's going to have a standard enthalpy of 0 in its standard state. All right, here's one for you to try. I'm wanting you to take this equation, 2Na solid plus 2 waters in the liquid state, reacting to form 2 sodium hydroxides, an aqueous solution, and hydrogen gas. Okay, so you take that equation. I want you to calculate the enthalpy of formation, the standard enthalpy of formation for this reaction. Now, I'm going to give you the enthalpies of formation of each of the constituent species there. Okay, so you have the standard enthalpy of formation for sodium is 0 kilojoules per mole because it's a pure substance. It's just sodium. We have water, H2O. It has a standard enthalpy of formation of negative 286 kilojoules per mole. And then we have sodium hydroxide with standard enthalpy of formation of negative 470 kilojoules per mole. And then the other species we have here is hydrogen gas, and it has a standard enthalpy of formation of 0 because, again, it's a pure substance. It's just hydrogen. So go ahead and pause the video. Try to come up with an answer for this. Be able to justify your answer. I hope you came up with negative 386 kilojoules. All right, and I would like to point out that if you did not get the correct answer, note that there are coefficients right here. So I'm not just going to plug in all of these numbers and let them fly. I have to correct for the fact that there are 2 sodiums, 2 waters, 2 hydroxides, or sodium hydroxide. So there are 2 of those. And also, if you remember the equation, it's the sum of the standard enthalpies of formation of the products, and then you're subtracting from the products the standard enthalpy of formation of the reactants. So it's these minus these. All right. And again, there are tons of sample problems that you can find. You can Google them very, very easily. Other YouTube videos would be a great help. But please do not skip reading the section. Your book is an invaluable resource here. All right. You're going to have one more video for this chapter. It's going to be a combination of sections 5 and 6. Please be sure that you attempt the associated worksheet. If you have any issues, try to solve them yourself. Use the book, use Google, use YouTube. And if you cannot come to an answer using those things, be sure you mark that problem and you have a specific question to ask me when we get back into class, and we'll spend some time working on that in class. All right, I'll see you next period.